Ladies and gentlemen, thank you for joining us for the Rank Prize Funds this evening for this, our 28th presentation of prizes. It's wonderful to see everyone, and I would like to welcome our prize winners who've made some epic journeys to be here, and also to welcome Professor Michele Dougherty, who is our guest of honour, to present the prizes. Michele, thank you. In the past, I may have welcomed you on a cold, snowy winter's evening. We now face rather different climatic challenges in the summer, and the challenge seems to be topical. Wherever we look, geopolitical, national political, economic and environmental challenges are there. However, this would not have surprised our founder, who lived through 2 world wars, economic depression, and towards the end of his life, some challenging UK politics. However, he maintained a strong belief that science and innovation would provide opportunities and solutions to find a way through these challenges. That is why he set up the endowment to recognise and reward great scientific research, to convene and bring together great minds and to support early career researchers. Anyone who knew him would recall his mantra that the young are always the seed corn of the future. He would not have been daunted by the headwinds that we see, merely looked towards his investment in research and development to support his industrial base of milling and filmmaking and to find a way forward. As ever, the selection of prize winners has been a demanding challenge, and I am indebted to Broadley and John Mathers for their deft chairing of the scientific committees, and the members of these committees are not only for their inspired selection tonight, but also through their diligent and well-judged application of these funds, both in supporting research and recognising the impact and application of the research. I believe our work remains current, hugely relevant, and supportive of the scientific research community. Sadly, not all our committee members could be here tonight, but I'd like to record our thanks for their outstanding support, as they, with previous years, they have selected our prizes and grants carefully from a wide spectrum of pure research. We have our 2 Lord Selborne PhD scholars present this evening, and we'll have their displays on research as we move back to the reception afterwards. We have also invited several of our early career researchers here tonight. They have presented at symposia and received wider grants. And we hope that being here, they will draw on the knowledge and advice of the Rank Prize Network, and some may come back in the future to lead symposia, mentor others, and I hope, possibly be the recipient of the Rank Prize in the future. I would also like to pay tribute to our small executive team who have worked so hard to keep the programme running over the year. They have organised an excellent prize giving tonight and maintained a full and well-managed schedule of symposia and wider grants. Since we last celebrated our prize giving, we have included 15 symposia, 27 undergraduate grants, 5 travelling bursaries, 11 ranked lecturers and 4 new lecturer awards. So team, and our financial team of Heather and Marco, thank you for what you have achieved. I'm immensely grateful for Professor Michele Dougherty to join us as our guest of honour and to present the prizes. She has served in many international universities and most recently with Imperial College through her work in space physics, and she is His Majesty's 16th Astronomer Royal. She has been engaged in 2 major space missions, NASA Cassini and the ESA JUICE spacecraft, pushing the boundaries of space exploration. Given her support to exploration of Jupiter and Saturn, one feels that the hyper-publicity of Messrs. Musk and Bezos on the Moon project is slightly overstated. She has been widely recognised in this field. In 2018, when appointed Commander of the Order of the British Empire, and through the Royal Society's Hughes Medal and the Institute of Physics Tree Medal. However, for me, the lay scientist, her appearance on Desert Island Discs brought her science achievements to life. So, Michele, thank you so much for carving out time in your very hugely busy diary, and welcome to the prize giving. We will now move on to the prize giving. First in nutrition, and I will ask Professor Malcolm Bennett to give the citation for the prize awarded to Professor David Salt and Professor Martin Broadley for their for their pioneering work on elemental profiling to improve soil and crop quality and enhancing nutrition and health outcomes for people worldwide. Malcolm.
It's a great privilege tonight to announce that Professor David Salt and Martin Broadley are the winners of the 2026 Rank Prize for Nutrition. Fusing advances in high-throughput elemental profiling with genetics, their groundbreaking research has revealed how plants accumulate mineral nutrients and trace elements from the soil. Their research is transforming dietary interventions in low and middle-income countries through profiling soil and crop quality to enhance nutrition and health outcomes. Micronutrient deficiencies, often termed hidden hunger, affect billions of people worldwide, particularly in regions where diets are dominated by staple crops low in essential minerals, notably in many countries in sub-Saharan Africa and Southern Asia. Professor Salt and Martin Broadley have led pioneering research to understand the dynamics of mineral elements in soils and plants, with a particular focus on the content of essential mineral nutrients in food crops and the impact on human health. Professor Salt from the University of Nottingham has been at the forefront of ionomics, the study of elemental composition of organisms. His research has revealed the molecular basis of how plants uptake nutrients that are essential for both plant and animals from the soil and distribute them through their tissues. These elements include cobalt, copper, iron, molybdenum, nickel, selenium, sodium, sulfur, and zinc, as well as potentially toxic elements, including cadmium and arsenic. Further, he's uncovered how these processes are influenced by genetic, physiological, and environmental factors. By identifying key genes and processes that control mineral accumulation, his work has laid the foundation for breeding crops with enhanced nutritional profiles. Professor Martin Broadley, the interim director of Rothamsted Research, I hope the full director in the short distance, has focused on translating the fundamental understanding of mineral elements in soils and crops into practical agricultural interventions and surveillance. His work spans soil and crop science through to nutrition and public health, with a strong emphasis on biofortification, using agronomic and genetic approaches to increase the concentration of essential nutrients in edible crops. His collaborations in several countries, particularly in sub-Saharan Africa and Southern Asia, has reported developments of regionally adapted crop varieties and farming practices that improve dietary mineral intake. So Professor Salt and Broadley have demonstrated that improving the mineral content of food crops is not only scientifically feasible, but also socially and economically impactful. Their research has informed national and international strategies to combat macronutrient deficiencies, including the use of macronutrient-enriched fertilizers in Malawi and the development of zinc-rich wheat varieties for Southern Asia. Their work is helping to shape food systems that are more resilient, equitable, and health-promoting. Congratulations.
I would now ask Michele if you can come up and present the prizes. First, David. And Martin. Get them back later. Right, sit back down. And now we would ask David and Martin to come up together and give a brief presentation on their scientific research. Thank you very much, Peter and Martin.
Well, thank you for that wonderful introduction, Malcolm, and for that wonderful award. I mean, it's blows me away. My appreciation for my peers is just wonderful. I must say, obviously, this is a joint award. What we're going to try to do is tag team. We've obviously got lifetimes worth of work here to try to share with you today, so it's going to be a journey that I'm going to try to compress into a fairly short amount of time, but hopefully it'll be interesting. It's going to be a journey across scales. I'm going to take you all the way from single elements, all the way through to the country scale, global scale, and public health, like I said, between me and Martin. So let's crack on. So actually this tale starts not only a single element at a time, but quite a long time ago. So as you can see here, a young whippersnapper, that is me. I actually still got that hat. And then here is also a kind of a dark and gloomy picture of Martin from Craven's NewsHour that he got off an old movie. Yeah, we started our work at a single element at a time, working on these amazing plants called hyperaccumulators. Got to thank Alan Baker is in the audience. He's one of the pioneers in this area. And we started out working on this amazing group of plants. Here's a Thalassopygus gengensi. It hyperaccumulates nickel. There are many other species that hyperaccumulate zinc. Has an amazing phenotype, and so we were very, very excited about studying that because obviously some of these elements like zinc are very important, and it made for a very, very interesting plant. We learned loads of stuff. Don't have enough time to talk about a lot of that, but long-distance transport, resistance, glutathione, vacuolar storage. We built up a lot of information about that. Also studied another super interesting set of plants. These are the Astragalus group that hyperaccumulates selenium to remarkable levels, 1% of their dry weight of selenium. And actually these plants accumulate, they biotransform the selenium, they accumulate into methylselenocysteine, which turns out to be a potent anticarcinogen. So I was very, very interested in trying to understand how you could take that process and actually develop nutritional supplements that were enriched in that compound. So that's Astragalus. We also worked on Pteris vittata, a fern. This thing hyperaccumulates arsenic. Can you imagine? We all learn about arsenic being super poisonous, killed Napoleon in the wallpaper, crazy stuff. This plant can hyperaccumulate in its natural environment 1% of its dry weight as arsenic. And here's Luke Gomerius, an old grad student of mine, done with a very close collaborator, Jody Banks, when I was at Purdue. Luke went out to Florida and made a big collection, and we actually studied the gametophytes as opposed to the sporophytes because they're a lot easier to manipulate genetically. Turns out these guys actually hyperaccumulate arsenic using a mechanism which is very similar to bacteria. So they actually are able to take up arsenic as arsenate. They trap it as this arsinophosphoglycerate, and then they use that as a way to transport it and store it in the vacuole. So doing super interesting stuff. So we were learning lots, but this was tough, slow work, one element at a time. And what we really thought we wanted to do is speed things up. And this was kind of in the era where genomes were coming out, high-throughput phenotyping was breaking, people were getting into genome-enabled genetics, and we wanted to stop doing stuff one element at a time and speed stuff up. And that's kind of where the idea of the ionome came in. We realized that actually plants, they're accumulating all kinds of elements, and so we needed to start to think about this in toto, not just individual elements. Pteris does arsenic, Thalassopy does zinc, Astragalus does selenium, but let's try to look at this in toto and use some of these kind of breaking technologies. And so we came up with this idea of the ionome and ionomics to try to get at that idea. So how do you do this then? How do you do multiple elements all at once? So a core to this was the development, as oftentimes is the case, analytical chemists busy trying to make cool machines. They're not quite sure what they want to do with them, but they're really cool. In this particular case, they built ICP-MSs, which essentially took the strength of ICP and mass spectroscopy and allowed you to measure all the elements essentially in plants in one go. And to do that pretty reliably and consistently in pretty high throughput. So we could do hundreds of samples a day. And this really opened up the idea that actually we could start to fuse genetics, which requires looking at loads of samples with high throughput ionomic phenotyping to start to get to genes. And so that was where we were, and that's kind of gone on from strength to strength in terms of citations. We developed a kind of whole community database around that, and we applied it to many different kinds of systems. So what were the benefits? And quickly, what did we learn from this? So you can kind of, obviously there's a ton of stuff to talk about, so I tried to break this down a bit into some kind of sensible pieces. So one of the great things about measuring multiple elements at a time is you can measure chemical analogs. So it's basically giving you 2 for 1. So you can measure potassium and rubidium at the same time, for example. And what that does, it gives you more confidence in the phenotype. And so here's an example of some work we did on trying to understand polyploidy and how it comes that it turns out that polyploidy is at the base of a lot of speciation. And it turns out anyway that, cutting a long story short, that these guys accumulate more potassium. It's very important for its osmolar balance. And by measuring potassium and rubidium at the same time, we could build up confidence in measuring lots and lots of samples. Another way to think about this idea of getting a 2 for 1 is zinc and cadmium. In this story, this is slightly different. It turns out that zinc is an essential element, cadmium is a potentially toxic element, and what we were able to do is by looking at cadmium, we were able to identify hidden genetic variation in plants, which is masked if you just look for zinc. Because zinc's an essential element, the plant regulates the zinc levels, even though there's a mutation in the homeostatic pathway, whereas for cadmium, it can't see cadmium, it doesn't want to take cadmium up, so it kind of reveals hidden variation. And so that was kind of fun. Another really cool thing about doing multiple elements at a time is you can start to identify multi-element signatures, so biomarkers, if you like, for particular alterations in particular processes. And so here's an example where we could see a big alteration in a whole bunch of elements, magnesium, calcium, nickel, potassium, and it turns out that very specific phenotype, ionomic phenotype, turned out to be disruptions in this very important process in roots, which are basically where the cells form tight junctions. So if you're familiar with tight gap junctions in gut epithelial cells, plants do a similar thing. They take a very different approach. There was very little known about this, and this method, this concept allowed us to unravel a lot of that stuff. Another great thing about doing ionomics, like I said, is it allows you to do high throughput, and so we were also able to start to access natural variation by looking at lots and lots of different individuals, a particular species. In this case, we used Arabidopsis thaliana. We were able to start to go and sample in the landscape and start to use that as a way to understand how do particular plants adapt to particular locations. Super important if you want to do precision agriculture, when you're going to do precision applications of fertilizers, for example. So this is Sylvia Bosham's. We did loads of work in Spain looking at salinity tolerance in Arabidopsis thaliana populations. Importantly, ionomics doesn't just work for so-called genetic model systems, but they also works for crops. And so we've applied that to primarily rice in my lab, but this is a great joint project, and this is a nice segue to Martin's stuff. And I'll tell you a very funny story very briefly, but Martin had a student, Thomas Alcock, who'd spent many years isolating a Brassica rapa mutant. I took one look at the ionomic phenotype and said that's Schengen3. It's a particular gene involved in some obscure process, but actually involved in this barrier. And it turns out Thomas went away and it was Schengen3. So you know, it works, right? It's great. And so this, I guess, is the segue to Martin's next part of the talk. And yeah.
Thank you.
Thank you.
One student actually. Oh, sorry. Yeah, applause. Sorry. What David didn't say, it wasn't one student, it was about 4, and it was about 12 years of a forward genetic screen that you'd solved, so thank you. So geonutrition. So we were struggling around 20 years ago to really understand baselines in terms of how these elements were getting into crops and into human diets. And from that period around 20 years ago, we started working, trying to understand a bit more about the landscape, soil, crop, climate factors on that. And before I continue, I would like to acknowledge the massive contributions of 4 individuals, UK-based individuals that are in the audience tonight, Murray, Grace, Edward and Alice, who've contributed hugely and are still contributing to this hugely in terms of developing the field of geonutrition. So geonutrition, it starts in the field. It starts with a huge amount of logistics, and this down here, this animation shows 8 field teams lined up there in Malawi, setting off and having to sample the entire country over a 6 to 7 week period back in 2018. And what they were doing is they were targeting specific sites that were designed using various sampling procedures to actually try and co-sample soils and the edible parts of crops in the field. The photo there is of hand threshing some teff in a field in Ethiopia, which was one of the other countries. What we were able to do from this approach, and this was the first time that this had been done at scale, at a national scale, was we were able to link directly soil and landscape features through to what was happening in the crop, through to what was happening in the diet, through to what was happening in the biomarkers of the status of that particular element. This is an example for selenium, which David introduced with the hyperaccumulators. Selenium is very important for immune function, and it's a critical element, and it's also present at very low concentrations in many diets. And those diets, if you're consuming food locally and you don't have enough selenium in there, you've got serious health problems arising. And I just want to acknowledge that there are so many collaborations around. This is Professor Daud Gashu of Addis University, who was the lead of the Ethiopia part of this work. In terms of what we do about that, in terms of how we try and intervene and scale the information from geonutrition, one of the ways that we can do that is through biofortification. Biofortification is either the enrichment of micronutrients in crops through breeding, through conventional or GM-type breeding approaches, or you can go at targeting fertilizers, or you can do both. And this is an example here of some basal fertilizer dressings on some maize crops in a field in Malawi. And what we were able to do is we were able to take the zinc national scale data that we'd collected and then work with the extension services and the fertilizer companies to understand these extension zones and then try and link it to both crop yield and quality, which I'm not showing, it's shown on this one, is the quality. And so this, for the first time, starts to then direct kind of commercially relevant fertilizer intervention strategies that the farmers can pay because it gives you a yield response, but also the government can support because it gives you a public health response. And Lester Botterman, who led this work in Malawi, he was one of the PhD students from the earlier phase of geonutrition working in the government of Malawi. This is the final case study that I'm going to show from the geonutrition work, and it's a fabulous piece of work, and it's a huge piece of work that was led by Rubel Alemu and colleagues at Tufts University in the US. What this scale map of Ethiopia shows, it shows the soil iodine concentration, but we also looked at crop iodine concentration and other dietary components as well. So the red areas here are where the soil iodine concentrations are low, and the blue areas here are where the soil iodine concentrations are high. Now, if you go back to the early 1990s in Ethiopia, there was an iodized salt program. So everybody in Ethiopia was having access to salt that was fortified with iodine as a public health measure to make sure that the iodine status of the population was measured. Salt iodization is a very long-known public health intervention. In around 1998, conflict started with Eritrea. And the iodized salt supplies were disrupted. All the supply chains stopped. And so individuals in areas of low iodine were resorting to locally produced salts without any iodine in it. And what Rubel has been able to do is he's been able to work with the geonutrition data and then look at health outcomes arising from children born after 1998. And there's just two examples here. This is child mortality rate. And this top line here is those kids that were born in areas of low iodine. And then this graph down here shows their exam performance. And again, this is kids grown in areas of low iodine, showing, say, adverse health outcomes, but also adverse cognitive performance outcomes as well. And so, taken together, what we can do is use the information on our variation in the crops and the soils and all those inputs going in and use it to inform agriculture and public health measures. Thank you very much. Oh, sorry. Before many acknowledgements to do. Should we go through them? Do you want to go? So Alan was also my undergraduate supervisor back in my undergraduate days. So it's brilliant that you can be here, and was a star of the John Craven's Newsround episode. And also I'd like to pay particular thanks to Philip White, who passed away in 2023. Thank you.
And then a couple of quick acknowledgements from me. So long-term collaborators here. So Mary Lou Guerino, I've collaborated with Mary my entire career on the ionomics concept. Charlotte Poschenrieder did all the work with her in Spain on all the field work, doing field experiments in Arabidopsis on the coast versus inland, and with Sylvia and others. Nico Geldner, long-term collaborator on the Casparian strip work, and then Brett Larner, who's a master's analytical chemist, and I'd say, he was the backbone of this whole concept. Without Brett knowing how to keep all those crazy biologists in track and do things in an analytical and careful way, I don't think we would ever got this off the ground. So yeah, then all the funders, and then obviously the institutions that have supported us over the time. And 20 seconds left. So maybe questions.
Timing, as W.C. Field said, is everything. Thank you very, very much, David and Martin. Now on to Optoelectronics, and Professor Jonathan Knight will give a citation for the prize awarded to Professor Susumu Noda for his work on conceptualization and development of photonic crystal surface-emitting lasers.
Thank you.
Jonathan.
Thank you. Good evening. This is a citation for the Rank Prize for Optoelectronics 2026. Professor Susumu Noda from Kyoto University is the winner of the 2026 Rank Prize for Optoelectronics. Over more than 25 years of dedicated research, he has developed a new form of semiconductor laser, the pixel, which combines the optical performance of more bulky laser systems with the efficiency, compactness, ruggedness or durability, and integrability of smaller semiconductor lasers. The pixel is an ideal candidate for implementation in areas such as high-precision manufacturing, autonomous vehicles where they need LiDAR, and space applications. Since the first demonstration of the laser in 1960, there have been continuous improvements in the performance and physical characteristics of the technology. In recent decades, optical fiber lasers and semiconductor lasers have been competing technologies, with both of these having a claim to being the most useful. With the pixel, Professor Noda has enabled semiconductor lasers to challenge the performance of fiber lasers in several key ways, including both optical performance and physical characteristics. The pixel builds on some of the known advantages of semiconductor lasers, the direct electrical drive, high wall plug efficiency, compactness, and ruggedness, but adds some key optical characteristics where semiconductors have not previously performed so well. The most notable of these improvements is the high power available from the pixel, combined with high beam quality or spatial mode profile, and the narrow spectral line width and controllability. The pixel does this by solving a problem affecting other successful semiconductor lasers, such as the edge-emitting semiconductor laser and the vertical cavity surface-emitting laser. In the edge-emitting laser, light passes horizontally through the gain layers of the semiconductor and is emitted from the edge. While in the vertical cavity surface-emitting laser, light passes vertically and is emitted from the top face. These lasers work incredibly well at low powers, but scaling to higher powers means increasing their cross-sectional area to get more optical gain, and it becomes hard or even impossible to control the profile of the light across this larger area due to issues such as spatial gain and temperature variations. With the pixel, this problem has been elegantly addressed by the introduction of a detailed pattern of tiny holes into the semiconductor material to control the shape of the optical mode, enabling the emission of high-power, high-quality beams from the top surface. Furthermore, manipulation of the complex pattern of holes enables the optical emission of any beam pattern or even electronic scanning of the output beam. This has required not only the use of high-precision technology at the forefront of modern engineering, but also a deep understanding of the interaction between such a pattern of holes, the so-called photonic crystal, and the light inside the laser. Across more than a quarter of a century of committed research, Professor Noda has identified the barriers facing the further development of the pixel and has invented ways for these to be overcome, bringing the pixel to the point of being application-ready and prepared for commercialization. Not only has Professor Noda led the research through this period, but he has improved the prospects for commercialization by building an extensive suite of patent specifications and through directly engaging with numerous businesses. His university-based Center of Excellence reports engagement with over 150 companies and institutes. In addition, he has recently established the Kyoto University Pixel Research Center to accelerate the societal implementation of pixel technology. The establishment and direction of businesses like Vector Photonics in the UK and Phototech in Taiwan indicate that many others see the value in this work as well. Thank you.
Professor Noda. And Professor Noda, over to you for a presentation on your research. Thank you very much.
Thank you very much. And it is truly great honor to receive such a prestigious prize. And I have spent more than 25 years on this research. And my research was recognized just like this. I'm very delighted for this recognitions. And today, I'd like to briefly review the photonic crystal surface emitting, surface emitting laser pixel. We call this pixel. So taking PCSEL, pixels. And we hope that these pixels will revolutionize the laser technologies. So the laser technology is important for realizing smart society represented by smart mobility and manufacturing. For example, laser-based LiDAR, where LiDAR expresses the light detection and ranging. So the laser pulse is irradiated various directions, and we measure the returning time. And then we can recognize where the obstacle is. And then the smart mobility of robot becomes possible. So laser-based LiDAR is also important for the smart mobility of farm machine, construction machine, and automobiles. Similarly, the laser-based processing is important for the smart manufacturing of electronics. So right now, the electronics is the air hose in electronics is made by laser. And also, the laser-based processing is important for the smart manufacturing automobiles. So the body of the automobile is cut by the laser. And maybe you know that the 3D printing. The 3D printing is also made by laser beams. However, the existing laser technologies have individual issues. So here I will show you that what are the issues of existing lasers. First, in conventional semiconductor lasers. So this is a very tiny devices, highly efficient. However, as shown here, the brightness is low. Brightness is low. So the low beam quality and large divergence, the emitted beam is much more diverse from the lasers. And the functionality is also low. For example, beam scanning cannot be achieved by themselves. Therefore, to deform the emitted beam from semiconductor laser, we need the complicated lens systems and fine adjustment, just like this. And to scan the beam, we need mechanical scanners, just like this. So even though the laser itself is very compact, but the system finally becomes complicated and large. Next, I will explain that the issue of CO2 lasers and fiber lasers. CO2 laser is just like this. So you can see that the size is meta size. And this is the fiber laser. It's also very large. And therefore, the cost becomes high, and also the functionality and the efficiency is very low. So we believe that the key to fix such issues of existing laser technology is in photonic crystal surface emitting lasers, as shown here. This laser has the structure just like this. So this is called the photonic crystals. So yellow portion, yellow circles indicated the air hole formed in semiconductor matrix. So we make air holes into semiconductors. And this air hole works as tiny mirrors. Therefore, the operational principle is as follows. So here you can see that magnified pictures. And the period of these tiny mirrors is equal to the light wavelengths inside the material. In this case, the light wave propagating to the upward direction is diffracted by tiny mirrors. And also, this light wave is diffracted to orthogonal directions. And this light is diffracted backwards. The real mechanism is more detailed and more complicated. So recently, I have wrote a very long papers. It's more than 50 pages. But anyway, this diffracted light interferes just like this. So this is a two-dimensional cavity mode. So white and pink is the magnetic fields, and arrows are electric fields. So this is just electromagnetic fields. The merit of this cavity mode is even though when we increase the device sizes, we can keep this very nice resonance. So this is the key to increase the high beam quality and narrow divergence. Actually, the individual air holes, so I mentioned that this works as mirrors, but also the nano antennas. The beam is emitted to your direction, surface emission occurs. And therefore, the laser beam emitted large area and coherently. Therefore, the laser beam does not spread. That's the key to increase the high brightness operation. So the brightness finally becomes to the bulky radar, such as CO2 radar, fiber lasers. And also, when we manipulating the individual air holes, then we can control the beam patterns. So even your face can be emitted from this device. Okay. So this is the history of pixels. So in 1999, we proposed this concept. So the solid progress occurs, and very recently we have invented this kind of the very unique structures. So the larger air hole photonic crystals and smaller air hole photonic crystals is overlapped. By using these structures, the 10-watt class or even higher power operation, high brightness operation was realized. And by using this structure, this is the dually modulated structure. So that you can see that the size and the positions are modulated. And by doing so, this device can emit any beam patterns. As I mentioned, your face can be emitted. Okay. So here I will show you more concrete example. First, pulsed high brightness operation for smart mobility of robots. So this is, as I mentioned, that a double latch structure, and the device size is very tiny, only 500 micron, 0.5 millimeters. And this very tiny device operated in pulse condition more than 20 watt. And then this is a comparison of the beam patterns for the conventional radars and pixels. And we put the screen at 1 meter apart, and the conventional radar already spread very much for the vertical direction. But the pixel is only very, very small spot. And even the 30 meter apart, still the very tiny spot. Therefore, we can make a very tiny LiDAR system. This is for LiDAR for robots. And you can see that the LiDAR is here, and the side is only the finger of even such a compact LiDAR, you can see that it will recognize the motion of the one finger or two fingers, just like this. And recently, we put this LiDAR, very small LiDAR, onto the carrying robot. This robot has pixel LiDAR here, and another robot has pixel LiDAR here. And this robot recognizes his movement and designed to follow this person. And the second carrying robot is designed to follow this robot. And you can see that just like this. It's very cute. So so the people come to our laboratories and push the button. Then the robot follows the persons. Okay. And next, I will show you that the continuous wave high brightness operation for smart manufacturing. So recently, we have developed this kind of the pixel. So these parts are the current injection part. The size is 3 millimeters. For semiconductor lasers, 3 millimeter is very huge because the size exceeds 5 micron. Then multimodal oscillation occurs. But in general, this size is not so large, very compact. But still, this device emits continuous wave lead of 50 watt. And the divergence angle is 0.05, almost no divergence. Therefore, the power is concentrated. And in reality, this laser can cut the metal just like this. Actually, this is the cutted result. And very recently, for this pixel is make arrays, and current injection produce the continuous wave 200 watt. And this can be utilized for the 3D printings, actually. So the company people want to use these very compact 3D systems. And very recently, we even increased the device size 1 centimeters. And 1 centimeter device can emit 500 watt. This is a pulsed condition. So the CO2 laser, 1 meter laser almost emits 1 kilowatt. It's very close to the CO2 laser. Even 1 centimeter replace the CO2 lasers. And very recently, we even continuous wave condition, the 300 watt single chip operation was realized. So now the CO2 laser will replace by this very, very compact lasers. Okay. And okay, so the pixel also emits, as I mentioned, a very unique beam. For example, by moving the position and change the size, then we can emit the Kyoto University from the 150 micron devices, or even emit here. This is a mascot in the Expo Osaka. Last year, Expo was held in Japan. This is a mascot, and maybe you know that these pictures, it's a great wave. So here the Mount Fuji, and this is a wave. And also you can see that the multi-dot pattern can be emitted. This is useful for the face recognition without any optics. And so far I have described that the wavelength is 940 nanometers. It's infrared regimes. But recently we have expanded even the blue regimes. This is, we utilize gallium nitride based devices. And also, when we use the indium phosphide based one, then the telecommunication wavelengths can be emitted. And this expansion of the wavelengths is now expected to revolutionize the even space communication. So this is some image. And in a space communication, conventionally, this type of large system is utilized because the semiconductor laser has not good beam quality. Therefore, this can be amplified other elements. It's a very big size. But the pixel can makes this very, very small. Therefore, the pixel promising ultra-compact light sources for space communications, including inter-satellite and Earth to Moon links. Maybe you know that SpaceX was recently stock. So they utilize this one. So we can use a very compact one in the near future. And actually, we started a collaboration with JAXA. JAXA is Japanese, like a NASA. Okay? And finally, I'd like to briefly mention about the bridging organization established very recently, 2024. This is for strengthening the social implementation pixels. And so far, we have in Kyoto University, inside Kyoto University, the Center of Excellence was established. And we supplied the pixel sample for various institutes or companies. But now, it's exceeding conventional university boundaries. Therefore, we established generally incorporated organization named Kyoto University Pixel Research Centers. This is completely independent from Kyoto University, and the business access is possible. So the people actually to ask this institute to device provision, also the equipment lending, and so on. So actually, I myself retired university at once, Department of Electronic Science and Engineering. Fortunately, I became the distinguished professors in another institute. That's a special institute in Kyoto University. But I at first considered that once I retired, then I become the more, I have more time, but in reality, it's much busier. Anyway, it's good for me anyway. And as such, I hope that the pixel technology expands smart society just like this, sensing, processing, mobile, communication, and so on. And thank you very much for your kind attention.
Professor Noda, thank you very, very much. Wow, huge applications there, I can see. Michele, thank you for presenting the prizes. You've also very kindly agreed to give some observations on the prizes, their interfaces with your experience in scientific research, space exploration, and possibly ABBA.
Thank you for that. Good evening, everybody. I was not going to mention desert island discs. But since the chairman has mentioned it twice now, I do feel that I probably should have been a little bit more professional when I was asked what my luxury item was. I'm afraid I asked for a solar-powered wine fridge. Instead of a telescope. I probably should have asked for a telescope, but I didn't. It's a great pleasure to be here with you this evening. I'd like to begin by thanking the Rank Prize and the Board of Trustees for hosting this event, and really for bringing us together to celebrate such outstanding science. The presentations that were given this evening, it is not my field at all, but I sat there in absolute awe of the work that you've achieved, so congratulations. The Rank Prizes have a uniquely important place in the scientific landscape. They recognize work that is not only excellent in itself, but which has the potential to make a real and lasting difference to the wider world. And it's that connection between curiosity-driven research, technical ingenuity, and societal benefit that's really something that the scientific community cares about. And it's so important that we are able to celebrate it. And so this evening, we've really had the opportunity to congratulate 3 remarkable prize winners. In nutrition, David Salt and Martin Broadley are recognized for pioneering work to improve soil and crop quality, and with the aim of enhancing nutrition and health outcomes for people across the world. And then in optoelectronics, Professor Susumu Noda is recognized for the development of the photonic crystal surface emitting laser. And that's really a powerful example of how an original idea can lead to technologies with really wide-ranging potential. I know that I am the last person speaking between you and the reception, so I'm going to keep this very short. I'll just say one final thing, and that's really, having now had the pleasure of presenting the prizes, may I offer my warmest congratulations to the evening's winners, and I hope you enjoy the opportunity to continue the celebrations and the conversations at both the reception and the dinner. So sorry about the noise. I don't think it was me. But thank you very much.
Michele, thank you so much. Well, if we do get stranded on a desert island, I think we've seen enough scientific research and innovation here which might help us go a long way. But we're not on a desert island here. We are in the Royal College of Physicians. If you'd like to, everyone who's here, like to go to the reception, which is out in the garden and where we were earlier on, there's some refreshments here. If the prize givers could stay for a little bit longer with the citation readers and for some photographs, and then we'll all join up together for the reception. Thank you all very, very much for your time, and I hope you've enjoyed this fascinating pair of prizes and the presentations which went with them. Very thought-provoking.